Hello everyone, I am Nikhil Kumar and I will explain digital signal processing project. This is our team. In our team there are three members: Nikhil Kumar, Gaurav Kumar, Sachin Kumar. This is our problem statement. According to this, I have to design a linear phase FIR band stop filter with some specifications. I can use triangular, Hamming, Hanning and Blackman window. I will show you the impulse response coefficient and I will plot the gain and phase response of desired filter for each case. I will also verify the results by filtering a signal. Here I selected some specifications like number of samples. I selected 100, sampling frequency 2000 Hz, lower cutoff frequency 200 Hz, higher cutoff frequency 500 Hz. Now, what is band stop FIR filter? A band stop FIR filter is a type of digital filter that is designed to attenuate the amplitude of signals in a specific frequency band. To design a band stop FIR filter, one approach is to use a windowing method. In this diagram, you can see here FL is our lower cutoff frequency and FH is our higher cutoff frequency. In between these two frequency, our gain is 0, so it is a stop band. Overall, the design of a band-stop FIR filter involves specifying the desired frequency response, selecting a window function, and then calculating the filter coefficients. Now one question comes in our mind that which window is better, Hamming window or Hanning window. Actually, the choice between the Hanning and Hamming window depends on the specific requirements of the application. If we want a smooth transition at the edges of the window and good attenuation of the side lobes, then we will prefer Hanning window. But if we want high frequency resolution is more important, especially for shorter window lengths, then we will prefer Hamming window. Here in this picture you can see that our Hanning window side lobes there is less ripples. The Blackman window is a more complex window function than the triangular window with three lobes that provide more attenuation of the side lobes than the triangular window. There are also many other window functions available, each with their own advantages and disadvantages. So it is important to choose the appropriate window function for the specific application. Now we will see our MATLAB code. This is our MATLAB code. In this code, here I selected some parameters n equal to 100, fc1 equal to 200, fc2 equal to 500, fs equal to 2000. Here I generate a test signal of frequency selecting 100 Hz, 300 Hz and 800 Hz. Here I using plot function to draw amplitude versus time and amplitude versus frequency for our test signal. After then I designed the filter coefficients for each window: Hanning window, Hamming window, Blackman window and triangular window by using each function. Like for finding the filter coefficients, we using function Han, HANN, and here a stop showing that we are making band stop filter. After then, for drawing filters, amplitude and phase response, we used FREQ function. After then we applying filter function to apply filters to the test signal. After then we draw here filtered signal. For drawing frequency domain, we are using here FFT function. For each window I am trying to draw filtered signal. After then here this code is for I try to create a file. In that file filter coefficients I will store all filter coefficients. Now you can see here in this filter coefficients file. Now this file is empty. When I will run this program, this file will automatically filled with filter coefficients. Now I am running this program. After running this program you can see here. Now I will explain one by one. Now you can see here this is our original test signal. In this here in between range of 200 Hz to 500 Hz, here 400 Hz frequency is present. This is our original test signal. After then, this is for Hanning window, phase response and magnitude response filter. Now this is for Hamming window, phase response and magnitude response filter. This is for Blackman window, phase response and magnitude response. And this is the magnitude and phase response for triangular window. After then, when we apply Hanning window filter on this test signal, we can see here, after obtaining filtered signal, here 400 Hz frequency attenuated, because it comes in that frequency range 200 Hz to 500 Hz. Similarly, when we apply Hamming window, also here 400 Hz frequency attenuated. Similarly, in Blackman window, here 400 Hz frequency attenuated. And in this original test signal, here 400 Hz frequency is present. Here, in after applying triangular window, 400 Hz frequency attenuated. Now after running the program, you can see here in this filter coefficient, here all filter coefficients get stored. For Hanning window, this is our filter coefficient. For Hamming window, this is our filter coefficient. For Blackman window, this is our filter coefficient. For triangular window, this is our filter coefficient. This is our result. A band stop filter was designed using 4 different window function: triangular, Hamming, Hanning and Blackman, with filter order n equal to 100, cutoff frequency set to 200 Hz and 500 Hz, and sampling frequency 2000 Hz. The frequency response of each filter was analyzed and plotted using MATLAB. The magnitude response and phase response of each filter were obtained and plotted as a function of frequency. The test signal was also passed through each filter, and the filtered signal were compared to analyze the performance of each filter. In discussion, you can see that the result of the experiment saw that each of 4 window functions produced a band stop filter with different characteristics. The triangular window produced a filter with the widest transition band, and the Hamming window produced a filter with the slightly narrow transition band. The Hanning window produced a filter with the narrower transition band than both the triangular and Hamming windows, while the Blackman window produced a filter with the narrowest transition band. However, the Blackman window also produced higher side lobes level than the other window function. The test signal passed through each filter shows that the triangular window produced a filtered signal with residual frequency in the stop band, while the other 3 window functions produced signals with no visual residual frequencies. Inference. In inference, based on the characteristics of the filters designed with each window function, we can infer that the Blackman window is the most suitable for designing a band stop filter with a narrow transition band. However, the higher side lobe level of the Blackman window may not be desirable for certain applications. The Hanning window can also be a good choice, as it produces a filter with a reasonably narrow transition band and lower side lobe levels compared to the Blackman window. In conclusion, mm, the experiment demonstrated that the choice of window function affects the performance of a band stop filter. The Blackman and Hanning window were found to be most suitable for designing a band stop filter with a narrow transition band, while the transition window produced a filter with the widest transition band. The Hamming window produced a filter with characteristics that were in between those of a triangular and Hanning windows. The choice of window function ultimately depends on the specific requirements of the application, and further experimentation may be necessary to optimize the filter design. Thank you.